Yeah.
Okay, great. Probably wait, I'd say 3 or 4 more minutes because on Fridays, the common schedule is that the classes are 50 minutes long, and then it's in until the hour, but we sort of teach all over campus, so people can be coming for break. So make the students active. That's much better than going back to LA or something to fly out of. Santa Barbara Airport is tiny little airport, very few lines or anything like that. I'm sure you've traveled through LA before. That's insane. Whatever.
It is, but the layout's pretty efficient.
Of LAX.
I think so.
I think, yeah, once you're in the right terminal, it's okay.
That's true. That's true.
I feel like the act of getting into the LAX, getting to the terminal is a challenge. Okay. Let's begin. So I'm very happy to introduce Sinho Chewi. Sinho is a PhD student at MIT under the supervision of Felipe Delay. Sinho was a recipient of the NDSCG Fellowship, and we're very happy to have him here to speak about 2 applications of reverse SDEs to sampling. Thank you.
Thank you very much, Katie, for inviting me and also introducing me. So I'll be talking about the idea of reversing an SDE and how this has been used for 2 recent applications to sampling questions. Please stop me at any time if you have any questions. So let me begin right off the bat by telling you what it means to reverse the SDE. Please move this. Okay, so suppose we have some stochastic differential equation, and for simplicity, we're just going to say there's just a drift and then Brownian motion. Then you can define the time reversal of this process. So I fix some capital T, the time horizon over which I'm going to reverse it, and then I just define this reverse process to be at little time at time little t. It's just the forward process at time capital T minus little t. So the amazing thing about this time reversal is that this backwards process is also a Markov process, and under some mild conditions, it also satisfies an SDE driven by Brownian motion. So this BT backwards, it's now like the reverse Brownian motion, but it still like has the law of Brownian motion. And the forward one and the the second one is the reversal of the forward one. Yeah. And also like the drift of the reverse process is explicit because it satisfies this relationship down below. So the the forward drift plus the backwards drift has to equal the gradient of the log density of the forward process at time t. And this gradient of the log density, it's called the score function. And this will be important in the top. So like for those of you who are familiar with the Fokker-Planck equation, I could give like a 30-second explanation for why this formula is true. If I want to reverse in time, then it's like I want to take the Fokker-Planck equation and I want to put a negative sign on the right-hand side. So how do I make the right-hand side negative? Well, if you look at the formula for the reverse drift, there's one term which is negative of the forward drift. So that will reverse the drift part of the Fokker-Planck equation. And then the score function, it will like cancel out the sign of the Laplacian and it will make the Laplacian term also negative. So this is why like this reverse drift gives you the time reversal of the forward process. And so this is I think it's pretty cool that there's this machinery for reversing SDEs. And what's surprising to me is that there's a lot of interesting applications of this idea. So overview of my talk, these are the two applications I'll talk about. The first is the proximal sampler, which is a recent algorithm that's been used for the problem of log concave sampling. And then I'll talk about score-based generative models, which are these like machine learning models that have been used to generate new images from scratch. I guess you've all probably heard about generative modeling. GANs are one way of doing generative modeling, but what I'm going to talk about is diffusion models, which is another way of doing generative modeling.
Which one's better?
Which one's better? So both have their positives and negatives. Diffusion models like take longer to run. They're more costly, but they're more stable because GANs have this like minimax training objective. Minimax training is just inherently unstable. So it's a lot harder to get GANs to work, whereas diffusion models are like more robust, I guess. And diffusion models, I don't know if you've heard of DALL-E 2. It's made the news recently because it's like amazing image quality. I'll give you an example later in the slide, but that's an example of what diffusion models can do. And I personally really like diffusion models because there's a lot of interesting theory that goes into them as well. So like, sorry to delay your gratification, but I'll start with the proximal sampler. All right, so this is some joint work with my collaborators, Yongshin, Adil, and Andre. Okay, and this was work done while we were visiting the Simon's program last fall. Okay, so the motivation of is there maybe I should. Okay, let's see if this works. Okay, so the motivation for this part of the talk and also for a lot of my research is that there's a lot of interesting connections between these two fields, between optimization and sampling. So in optimization, what we want to do is we have some function v and we just want to minimize v. And in sampling, what we'd like to do is we'd like to output a sample from a target distribution, pi, which has density proportional to e to the minus v. So these two problems turn out to be analogous to each other in many ways. And it's the connections between these fields that have spurred a lot of recent research. So to explain this connection, let's start with maybe the most basic algorithm for sampling, which is the Langevin diffusion. So Langevin diffusion is the solution to this SDE. And if you look at it as two parts, the first part by itself just is a gradient flow for V. But then we also have to add Brownian motion because in sampling, we don't just want to get to the minimizer of V, we need to explore the entire distribution. And you can show that this diffusion has pi, which is of the form e to the minus v as its stationary distribution. That makes it a very good candidate algorithm for sampling. So on first glance, like this diffusion, it looks like a noisy gradient flow. So that's one way in which you might think of this diffusion as the analog of the gradient flow in sampling. But there's a much more interesting way to view this as a gradient flow. And this is this perspective that was introduced in seminal work by Jordan, Kinderler, and Otto. And what they observed was the following. So pi t is going to be the law of xt. law of the process at time t. And if you look at this curve of probability measures pi t, then it turns out to be a gradient flow of this functional over the space of probability measures. It's the KL divergence to the target measure pi. And when we talk about gradient flows, we also have to specify a geometry on the space we're looking at. And this geometry turns out to be the geometry of optimal transport. Namely, we equip it with the 2 Wasserstein distance from optimal transport. So what does it mean to follow a gradient flow? So like in quotation marks, it basically means that the evolution of the marginal law of the Langevin diffusion follows the minus gradient of the KL divergence, where this gradient is taken in this Wasserstein sense. But in order to really make sense of this, we need to understand like how do we define Wasserstein gradients and how do we like what does it mean for the time derivative of the density to equal this right-hand side? So this original paper of JKO, what they did to make sense of this was they showed essentially the following, that if I start at pi t and I just look a short time eta later, then the law of pi t plus eta, it approximately solves the following optimization problem. We minimize the KL divergence plus like 1/2 times eta, which is like the step size, and so the squared Wasserstein distance to the previous target pi t. And so this is known as the JKO scheme after your paper. But if you're familiar with optimization, then this has a name in optimization. This would be known as the proximal point method, or an implicit discretization of the gradient flow. So the nice thing about this approach was that in order to define this JKO scheme, you only need like the metric. You don't need to get into all the calculus machinery yet. So let me just review the proximal point in optimization. The proximal point method, this is the method for optimizing V, and you just iterate this proximal mapping. The proximal mapping is defined very similarly to what I showed in the previous slide, but now we're on Euclidean space. You just minimize V plus a quadratic term. So this proximal point method, it's one discretization of the gradient flow, but it's an implicit discretization because you can show that it reduces down to this iteration, which means we're evaluating the gradient at the next iterate rather than the current iterate. That makes it harder to solve for in practice, but it also means that this discretization is much more stable. And one way of implementing this algorithm is, notice like we added a quadratic term, and as the step size gets very small, this quadratic term is dominating. In particular, as long as V is smooth, just that its Hessian is bounded, as long as I choose the step size small enough, this proximal mapping is going to be a strongly convex and smooth problem, which is exactly like the class of functions for which we have a lot of like extensive algorithms for. So the moral is like choose a small step size, then we can use any of our like favorite off-the-shelf optimization algorithms to compute this proximal mapping. So what I want to ask in this first part of the talk is, what is the sampling analog of the proximal point method? Because we have all these like connections between optimization and sampling, can we sort of take the idea of the proximal point method and bring it into the sampling context? And I already kind of do this. It's this JKO scheme, because the JKO scheme, it's just like iterating this proximal operator for the KL divergence in Wasserstein space. But the issue with this scheme is that it's not implementable, because a single evaluation of this proximal operator requires solving an optimization problem over the space of probability measures. It's not really any easier than the sampling problem we're trying to solve. There's another approach, which is called the proximal Langevin algorithm. This is just trying to incorporate the proximal mapping into the Langevin algorithm. So instead of taking a gradient step on V, as we would do for the Langevin diffusion, we instead replace it with the proximal mapping for V. But this is kind of unsatisfactory. So both the Langevin algorithm and also this algorithm suffer from the same problem, which is that there's asymptotic bias. What I mean for that is that for any choice, positive choice of the step size, the stationary distribution of this Markov chain is not equal to the target distribution pi. So by discretizing the diffusion, we introduced some bias, and that's not very satisfactory. So can we do anything better than this? And there's an interesting answer to this question, and it's given by the proximal sampler. The proximal sampler was introduced in a couple of earlier works. And here's the idea of the algorithm. We're first going to augment our target distribution into a joint distribution over the variables x and y. And this joint distribution, it's like proportional to e to the minus b. And then I've also added like this extra quadratic term to the density. So this should start to like remind you of the proximal point method. And for this target distribution, we're just going to do Gibbs sampling. So what is Gibbs sampling? Gibbs sampling just alternates between sampling from the conditional of x given y and sampling from the conditional of y given x. So explicitly, given an iterate xk, we draw yk from the law of y given x. And if you look at the law of y given x from this target distribution, you'll see it's just a Gaussian distribution centered at xk with variance eta. So this first step of the algorithm is very easy to implement. And in the second step, we have to sample from x given y. Now, this second step, it's not explicit, so it's not clear exactly how you implement this second step. So for now, think of this as a conceptual algorithm. So this second step, in order to implement the proximal sampler, we need to assume that you can perform the second step. So we call the second step an oracle. And in this paper by Li Shen and Tian, they call it the restricted Gaussian oracle, or RGO. Okay, but if you assume that you can implement the RGO, then this algorithm is unbiased for this augmented target distribution. And that's just because Gibbs sampling is just always an unbiased algorithm, just a general property of Gibbs sampling. And also the x marginal of this distribution is going to be equal to e to the minus b, the original distribution we want to sample from. Okay, so some questions I have to answer in order to convince you that this is not a crazy idea. First of all, I have to tell you how to actually implement the RGO, otherwise this is not an algorithm. Second thing is I call this the proximal sampler, and I'm really looking for an analog of the proximal point method. So why should we think of this as an analog of the proximal point method? It seems like it seems less close to the proximal point method than the other two candidates I listed in the previous slide. And the third question is, we gave an algorithm, but can we actually show convergence guarantees for it? So we're going to address these three questions in order. Let's start with the implementation of the RGO. So again, I'm going to assume that V is smooth, which just means that the Hessian is bounded. Then this is the same exact story as for the proximal mapping, where I've added this like quadratic term. So if the step size is very small, then this becomes a distribution which is called strongly log concave and log smooth. That means like if I take the log density, then that's smooth, and also the negative log density is strongly convex. So this class of distributions, known as a strongly log concave and log smooth, similarly to optimization, this is like the class of distributions for which it's easiest to get convergence guarantees for sampling algorithms. There's a lot of different samplers you can use to implement the RGO. But in fact, like if you choose the step size small enough, then even just a very simple rejection sampling algorithm can implement this RGO. The point of this slide is like, for the rest of this talk, let's just say like, okay, we can implement the RGO with some choice of step size, and let's like not worry about the implementation anymore. Now I want to talk to you about the analogy between this algorithm and the proximal point method. So recall that the analogy I showed at the beginning was in optimization, we minimize V. In sampling, we sample from e to the minus v. So if you just apply this analogy to the proximal operator, then you'll see it's exactly analogous to the RGO. So that's one way in which the RGO is kind of an analog of this proximal operator from optimization. There's another cool interpretation, which is that you can show that this RGO distribution, it solves this optimization problem. And this optimization problem, this is exactly the proximal operator for the KL divergence but evaluated at the Dirac measure, centered at Y. So somehow like this assumption that I made for the proximal sampler that we can implement this RGO, this is equivalent to assuming that we can compute the proximal operator on Wasserstein space, but for a restricted class of measures, for Dirac measures. And it's the fact that we're assuming that like this restricted class of measures that is like key for the implementability of the RGO. Okay, so now I want to talk about the convergence of the proximal sampler. And to do that, I'm going to draw some analogies with the Langevin diffusion. So the convergence of the Langevin diffusion has been studied under a variety of assumptions, such as like the strong convexity of B, the convexity of B, or certain functional equalities like the log-Sobolev inequality and the Poincare inequality. And these functional equalities allow for a little bit of non-convexity. And all of these like inequalities have very interesting interpretation. So there's like entire books written about the convergence of Markov processes. And these four assumptions that I mentioned all lead to convergence guarantees for the Langevin diffusion in various metrics, like the Wasserstein or the KL divergence or the chi-square divergence. So I don't need you to like memorize this slide right now, just letting you know that, okay, there's like a bunch of classical conditions under which we study the Langevin, and they lead to different convergence rates for the diffusion. So the question is like, can we get something like this, but for the proximal sampler? So just a bit of notation, mu k x, this is going to be the iterate of the x variable. Remember the proximal sampler, there's like a x and a y and we alternate. So mu k x is the log of the x variable at iteration k. So the first result that was shown in this paper by Li-Shen Chan is under the strong convexity of V, they're able to get some Wasserstein contraction of your iterates to the target distribution. And one cool thing about this result is that it's exactly analogous to optimization. In optimization, you can prove that if your objective is strongly convex, then this proximal mapping is a contraction, and you can see these contraction factors exactly line up. That's very cool.
Sure. Can you say again what alpha?
Alpha is the strong convexity parameter of V. Like I'm assuming that the Hessian of V is uniformly lower bounded by alpha.
Oh, I see, given by the uniform.
Yeah. Okay, so now in our work on this problem, what we do is we basically show all the other convergence results for the proximal sampler. These are the other three settings I mentioned for the Langevin diffusion, and we get these results for the proximal sampler. And just it's so amazing to me just how like clean these results are and how they really like they're really like as sharp as can be, because you can see that these contraction factors are exactly the same ones that I showed on the previous slide. And this like this first result, it's a convergence that behaves as 1 over the number of iterations, and that's exactly the convergence result in the convex case for Langevin. So somehow like this is the slide that convinces me that the proximal sampler is the right analog of the proximal point method for sampling, is because like it has all the properties that you would expect out of a proximal point method for sampling. So as I mentioned before, if your potential is smooth, then we can implement this RGO, for instance, via rejection sampling. So if you combine together the convergence of the proximal sampler together with the implementation, then you automatically get a lot of complexity guarantees. For instance, here, like I'm just showing one example. Suppose you satisfy Poincare plus smoothness, then you can get some chi-squared guarantee, and you can write down very precisely what is the number of iterations that you need. And this particular corollary happens to be like a state-of-the-art guarantee under these assumptions, but I'm not really like here to discuss that. But I will like sort of mention like why I think this algorithm is very useful for sampling. So here's just like three nice points about it. One is that the discretization for the proximal sampler is actually kind of trivial. As I mentioned, like it's all just about implementing this RGO, and you can even do that with rejection sampling. Somehow like there's no like discretization to do. Whereas like for the Langevin diffusion, you need to first choose a step size, you need to discretize, then you need to write like a 40-page paper in order to understand how like the discretization error propagates in time. And like because the discretization analysis can be challenging, like sometimes the rates for the Langevin diffusion are not as sharp. And that's like one reason why this proximal sampler gives state-of-the-art guarantees. Another cool thing is that the Langevin algorithm, it requires acquiring the gradient of your potential. Whereas like for the proximal sampler, depending on how you implement the RGO, you can implement it in a way that doesn't require the gradient. And this is very important for applications to like Bayesian inverse problems where you really don't have access to gradients because like the potential is like the forward map of a PDE or something like that, and it's too expensive to compute gradients. And also like, and I mentioned this proximal sampler is unbiased. So this leads to like faster algorithms than the Langevin, which suffers some asymptotic bias. Yes.
Can you say a little bit about what eta is in this context? I forgot.
Eta is the step size.
Oh, the definition of the
RGO.
Okay, great.
Yeah.
Mhm.
So there's a trade-off where I want to make eta small in order to make this RGO easier to implement, but I want eta to be large so that the overall algorithm will converge fast. But then we pick the step size to kind of balance these two considerations.
It can, is it still converging to the same dynamic design in the limit that eta goes to 0?
Yes. Okay, so now I want to comment on some aspects of the proof of these convergence results. And this is where the idea of reverse SDEs is going to come in. So let me start by reviewing at a high level how we analyze the Langevin diffusion. So in the Langevin diffusion, we just say like compute the time derivative of the KL divergence along the Langevin diffusion, and you can get this formula. You get on the right-hand side a quantity which is known as the Fisher information. Now this like log Sobolev inequality that I mentioned, it's precisely just assuming that the Fisher information upper bounds the KL divergence. So if you just combine these together, you immediately get that under a log Sobolev inequality, we have the exponential convergence of the KL divergence. Okay, so that's a pretty simple proof scheme for the Langevin. We want to do this for the proximal sampler. In order to do this for the proximal sampler, it really helps to have this stochastic process interpretation of what's going on, because that allows us to do calculus. So this is going to be the stochastic process in the proximal sampler. It's just a Brownian motion, but the Brownian motion is started at pi x. Now, this augmented target distribution, which was like, I took e to the minus v and then minus the quadratic. This is actually exactly the joint law between x0 and x eta of this process. And that's because like the solution to the heat flow is just like a Gaussian centered at your original point. So if you just write down what is the joint law of x0 and x eta, it's like the log of x0 times like this Gaussian for x eta. So you get exactly this augmented target distribution. So what does that mean? It means that the two steps of this proximal sampler have an interpretation in terms of this stochastic process. This forward process, which is y given x, it's just going to be x eta given x0. And similarly, x given y, this is going to be x0 given x eta. And for the second one, you can see the backwards conditional law. So when I talk about the backward step, that's where we're going to talk about reversing the SDE. But let's start with the forward step. So now that we have the stochastic process, turns out you could do something very similar to before, where I compute the time derivative of the KL divergence. QT is like the heat semigroup, the evolution along the whole process. But one difference is that instead of just like the KL divergence to a fixed target, I'm evolving both the target distribution and the iterate of the proximal sampler together with the heat flow. But when you do this computation of the KL divergence simultaneously in both arguments, you actually still get the Fisher information, just evaluated at the right arguments. So it's a pretty interesting computation. This is a schematic of what's going on. So pi x is the target distribution, the x marginal. You run it through the heat flow and you get pi y. And similarly, like you have the x X law for the proximal sampler, you evolve by default and you get the law of Y in one iteration. And this calculation tells us that these two paths are getting closer to each other. So similarly to before, if you assume like a log-Sobolev inequality, then you can actually solve this differential inequality and you get some contraction in the KL divergence along the forward step. And the backward step is actually completely analogous. It's just that instead of the heat semi group, we need to consider this QT with the backwards arrow. This is corresponding to the backwards process. And you can also do these calculations and they turn out to be very much the same. And in the backward step, we're going from from Y to X. And the iterate of Y in the proximal sampler becomes X in the next iteration of the proximal sampler. So just a few words about the backward step. What is this QT backwards? Well, remember in the backward step, we want to look at the law of x0 given x eta, which is backwards in time. It's a little bit more natural to think about reversing the SDE. So we can now think like forwards in time for the reverse process. We reverse the process, and now because of what I told you on the first slide, this reverse process is completely explicit. And this is what allows us to do the calculation for the backward step as well. Here's just a schematic of the overall proof. You have the forward step where they both get closer, the backward step, they also get closer, and you change together these inequalities and you get the KL convergence, for instance. And there's like a little bit of a general principle going on here where if you have some kind of functional quality which implies convergence of Langevin, it probably can be put into this proof scheme and also gives you convergence of the proximal sampler as well. Right, so this is like kind of encoding the idea that the proximal sampler is like a very stable discretization of the Langevin diffusion somehow. And I can't resist like mentioning that this idea of the proximal sampler has actually like showed up in various areas of math, especially with regards to this like Kanan-Lovar-Simonovitz conjecture, which is an important conjecture in like convex geometry and high dimensional probability. So there's this paper by Hartag and Puderman, which identified a connection between these three objects, which are like common tools in high dimensional probability. There's this like Fulmer process. There's like this technique of stochastic localization, which was introduced by Eldon to prove a lot of striking results in probability. And they connect in this paper, they connected these two with what they call the adjoint of the heat semigroup operator. Then like in this paper by Yuanxi Chen and Ronan Eldon, this paper actually shows that these ideas are also essentially the same object as the proximal sampler, which is pretty funny. And using this, there is this very recent work by Hartag and Lehed, which makes like breakthrough progress on the KLS conjecture. Now they show that the KLS conjecture is just polylogarithmic in the dimension and dimension D, which is like very inspiring progress on this problem. Yeah, I mean, it's really cool that there's all these connections, but also like maybe this just shows that the proximal sampler is a very natural construction and might be like useful for further advances in mathematics. So here's a quick summary. The proximal sampler, it's the sampling analog of the proximal point method from optimization. And what we do is like we show some new convergence results, and these convergence results happen to be like some state-of-the-art results for sampling. Are there any questions so far? So I have numerical examples. No, I do not. Sorry. I have talked to Shen from Li Shen Chan, and she implemented it and she said it works very well.
Just curious as to how double well potential, how well.
Right. Well, definitely our results are more for like the unimodal or close to unimodal. I think like, so it depends on the step size. If your step size is very small, it'll be very similar to Langevin, so it'll be hard to jump to the other well. If you take a large step size, it could actually jump across, but then you have to worry about the implementation of the RTO. And actually, that's very related to the second part of the talk. So I think I'll defer that question. So then.
So I was confused. So how did proximal sampler remove the bias? It was through rejection?
It's because like the algorithm is Gibbs sampling, and Gibbs sampling just like whenever you have a joint distribution and you sample from one conditionally on all the other variables and you iterate this always forms a Markov chain which is reversible with respect to your target distribution. So yeah, just by construction, it just always is unbiased.
I'm just trying to like, obviously I always do these things in terms of like dynamics and like time step or time discretization, space discretization and stuff. Clearly, like a really nice thing you did here was you got rid of bias from the time discretization. Is there a sort of interpretation like you're replacing the time discretization with the spatial discretization in the second dimension?
Replacing the space.
Or just like the fact that you're going to now you're looking at a probability and a product space and sampling and X and sampling and Y. Is that like no, that may not make sense.
Yeah, I'm not sure. I think I'd have to think about your question some more.
Okay, yeah, anyway, I just think it's very interesting how you're able to remove the time discretization.
Yeah. Okay, so now I want to step back from the proximal sampler a little bit and take a slightly more general view. And this general view is actually going to lead us into the second part of the talk. So in the proximal sampler, we start off with some forward process, and the forward process was just Brownian motion, but we didn't need to just consider Brownian motion. You can consider some arbitrary SDE for the forward process. You could take its time reversal for the reverse process. So what happens if you consider other choices here? In particular, one very nice choice here is what's called the Ornstein-Uhlenbeck process. It's the solution to this SDE. So this SDE is very special. Its stationary distribution is the standard Gaussian distribution, and we all love the Gaussian. It's maybe like the unique Gaussian Markov process whose stationary distribution is the standard Gaussian. And it's an instance of the Langevin diffusion when the target is the standard Gaussian. Okay, so this is a very natural choice for what we can take as the forward process. And now there's something very nice about the OU process. By the way, in the second half, I'm going to change notation a bit. Sorry about that. So in the second half, for instance, I'm starting at the distribution which will now be called Q, and QT is the law of the forward process. So the OU process, it's known that it converges to the standard Gaussian very quickly, exponentially quickly. And this convergence holds in like a lot of the metrics you can think of, factor sign, KL, pi-squared, and so on. So this is the schematic. I start off with some distribution Q0. I run it by the OU and get very, very close to the target, to the Gaussian distribution, which is a stationary distribution. And now like consider reversing this process. So up here, like remember, this is the calculation that I did for the backwards process for the proximal sampler. If I compute the time derivative of the KL backwards in time, then I get like a minus Fisher information quantity, and that quantity is just always like negative. So what that means is that the backwards process, it never makes the processes diverge apart. It can only bring the backwards, the two processes closer together. And this is like an instance of what's known as like the data processing inequality in probability in stats, which just says that if you like apply the same operation to two probability measures, then they can only get closer in scale. Okay, so this is the schematic. Like the forward process brought Q close to Gaussian. Now the reverse process, it can only bring them closer. And this chain of inequalities is just like writing down what this picture is saying. So this is the KL divergence between Q and the reverse process started at the standard Gaussian, which is these two dots. It can only be closer than what the two processes were at the start. And the two processes at the start were very close together because of the fast convergence of the OU. So what is it saying? It's saying like if I want this sample from Q0, then I could start at a standard Gaussian and run this reverse process, and I'm going to get very close to Q0. So the question now is going to be like, can we actually implement this reverse process? Okay, so from the perspective of the proximal sampler, what's going on here is like we initialize the backward step, the RGL at the standard Gaussian, and just one step of the backwards process is already enough to kind of converge. But the real question here is like, how do we actually implement this? And this is going to be the idea of score-based generative model from my perspective. And my perspective is we just need to discretize this reverse SDE. And the way that you discretize the reverse SDE, remember that the reverse SDE always involves a score function when you reverse in time. So this score function is something that's going to need to be estimated on the basis of samples. All right, so let's get into it. This is some joint work with a bunch of collaborators. This was done last summer while I was a research intern at Microsoft Research. Okay, so just like this is an obligatory slide in case you're not familiar with the amazing things that score-based generative models have achieved in recent years. This is the magazine cover of Cosmopolitan, and this image was completely generated from pure noise by AI. So what happened was like someone from Cosmopolitan typed in like a sentence, something like astronaut striking cool pose, split in front, scene shot from below, and it just generated this image, starting from pure noise. The pure noise is the Gaussian distribution. We run the reverse process, and we get to this image. And this is just like one of the examples of just how like amazing these diffusion models are. And now like they're so amazing that they're starting to be like commercially used by artists. Like artists can like interact with these systems and like produce useful output like this. So what we want to do is understand these models a bit more. Okay, so as I mentioned, in my perspective, I want to discretize this reverse SE. So this is just what I get when I apply this time reversal process to the Ornstein-Uhlenbeck process. I negated the drift, so minus XD becomes positive now, and I also have the score function showing up. So this is the SDE that we want to implement.
Just clarify, so are we still on the second half of the green flow or the B drift can we get it now?
B is still Brownian motion.
I mean, the drift that you showed on the right there first time. Are we still on the grading flow? That means the grading E or can be anything.
Like if you want, you can think of it as I want to sample from Q, which is like of the form E to minus E.
Yeah, I just want to verify the SDE form that we are working with.
It's this SDE.
Okay.
So somehow like the grad V is hidden in here because at time 0, grad log of the density is going to be like the gradient.
So we are still working on with grad V.
Yeah. Yeah. Okay, so we want to implement this reverse SDE. The difficulty is that we need to now estimate the score function. Okay, so let me back up a little bit. Like for the application of generative modeling, Q0, think of it as your distribution over images. And we want to like generate new images from noise, which is like saying we start with the Gaussian, we run the reverse process, we generate a sample from Q. Okay, so the problem is we don't know what is the distribution over images. We don't know Q0. In particular, we don't know the score function grad log Qt for any time t. So how are we going to implement this? So the way that we do it is we're going to approximate the score and we're going to learn it via neural network. So script F, this is going to be like your favorite class of neural networks, like a parameterized class of functions. And imagine that we want to learn the score function by just setting up an L2 loss. We want to find a minimizer in the function class ST that's as close as possible to the score. Okay, but this objective, we still can't use it in practice yet because we don't know how to evaluate grad log QT. But there's an integration by parts trick. Integration by parts, one of the most powerful tools, you know. So when you apply it in a clever way, you could reformulate this objective as this objective. So here, like x0 is a sample from Q. So think of x0 as like an image, a natural image. Then xt, this is like the noise version of the image because vt is just a Gaussian variable, a noise variable. So I take like a noisy version of it, of the image, and this problem has like an interesting interpretation now. It's saying I want to learn a predictor st, which takes in my noisy image xt and predicts what was the noise vt that was added to an image. So this is what like machine learning people will say when they try to explain SDEs. They'll say like, oh, we're training the neural network to be able to predict the noise that we fed it, starting from the noise image. But yeah, it really just comes from this L2 loss and the integration by parts trick. And then
Only or for other?
so like for every forward process that you can think of, you need to like figure out how to do this trick, I guess, if you want to
Just particular computation.
yeah.
That's what we-
yeah, this is for OU. So the nice thing about this is like now we can replace this expectation with the empirical average over samples. And so these samples x0, these are just like your database of images. So for my database of images, I add noise to them to form like the noisy images xt. I also have the VTs, which is the noise I added, and now this is some objective that I can train with the neural network. And I learned some score. So this is how you set up the score learning problem. And now once you've learned a score function, what we do is we take our reverse SDE and we substitute the score function with this learn score, little s. And also I discretize it. So I'm supposed to have there like the score at time like capital T minus little t. But instead of doing that, it's going to freeze this coefficient at multiples of the step size h. And the reason why I do that is like, now if you look at this SDE, this is like a linear coefficient, this is a constant now. So it turns out like you could integrate this SDE into a score. So this is something you need to do if you want to numerically influence SDE, you need to do that. So now we have this algorithm and we're going to initialize this at the Gaussian. But just to be clear, like what are the sources of error in this algorithm? There's like 3 sources of error. One source of error is that we're initializing at the standard Gaussian, but we're supposed to be initializing at like QT, the where the forward process was at time t. But we're saying, okay, the forward process, it got very close to the Gaussian, so we're just going to initialize at the Gaussian. So that's source of error number 1. Source of error number 2 is that we're estimating the score function via unknown output. Source of error 3 is that we're discretizing the SDE. So we're only approximately implementing it. So the work that I've done on this topic is just trying to understand how do these like 3 sources of error propagate in the sampling error. Right. So what I look at in this work, I just want to mention like I am not trying to quantify how well the neural network learns a score. Instead, I'm just going to say like if the neural network learns an epsilon accurate score, how does that translate to the sampling error? So actually, like I think this first bullet point about how neural networks learn the score, this is actually the most important part, right? It's like the magic of this whole thing is just that neural networks can learn things to scary amounts of accuracy. But it's also a very complicated question because you need to understand the optimization dynamics and so on. So I'm not going to address this. Instead, as I mentioned, I just want to see how these sources of error propagate in time. So there's some stuff about prior work. I mean, I won't really bore you with the comparisons. Let me just tell you like our assumptions and our results. So these are like our 3 assumptions that we make. The first one is that the score function is Lipschitz. The second is just that the data distribution has some finite second moment. And then like this is the part where we treat the neural network as a black box. We're going to say, let's say the L2 error of the learned score is going to be some epsilon score. Then how can we get error bounds that depend on this epsilon score? And this is like our main result. The total variation error between the law of the score-based generative model and our data distribution can be decomposed into these like three terms. The first term is the convergence of the forward process, and this goes down exponentially fast because the forward process is converging very fast. You have the discretization error, which this goes down as you choose the step size h to be small. And then the third term has this epsilon score, so this is measuring how well you learn the score function. But the error bound you can very cleanly into these three terms.
The metric of the distance. Total variance.
Yeah, this is total variation.
I mean, no longer like the process had that work before.
Yeah, it's not us. You're saying total variation is just most convenient for this instance.
And if it's metric, it won't work. Actually.
Yeah, definitely our proof would break down. For Wasserstein, you might be able to use some kind of truncation argument to say something, but yeah, this result is just for TP. Okay, and what is the corollary of this? Let's say that your score estimation error is smaller than some epsilon, and you choose like the step size and the total time t correctly. Then basically it also gives you a precise estimate for the number of iterations that you need. And it's like Lipschitz constant squared and the dimension divided by epsilon squared. So the nice thing about this is that this is like a polynomial guarantee in all of the parameters. And one thing that's special about this setting is that I made no assumptions about the like log concavity of my target distribution. In particular, the distribution could be like highly multimodal. It can cover like the double well situations that you were asking about. The catch is like everything is kind of hidden in the score approximation. Like in order to sample from these double wells, you'd of course need to learn the score function of those double wells. But this is just saying like if you had this omniscient neural network that can learn whatever score you want to, then in principle these diffusion models can sample from like a broad class of very like non-log concave distributions. Just to contrast this with Langevin, like the problem with Langevin is that in order to jump from well to well, it can take exponentially long time to do so. So there's no such issue here. And here's another corollary, which is before I was assuming that the score function is Lipschitz. And in order for the score to be Lipschitz, I need my distribution at least to have a density with respect to the Lebesgue measure and so on. But actually in machine learning, there's this thing called the manifold hypothesis, which is saying actually your distribution over images is supported on a lower dimensional manifold, something like that, in which case like you would definitely not have a Lipschitz score. But you can formulate this corollary. So Q is now an arbitrary distribution with compact support. Then it's not possible to get just TD guarantees anymore. The reason why is like your data distribution could be supported on a lower dimensional set. The law of your algorithm will be fully supported, so the TV distance will be trivial. But you can say you're close in TV to something that's close in W2. I know that's a little bit weird to say. And you get this like, and everything scales polynomially. So where does this probably come from? It's just because like in the forward process, you're running the OU, and if you just run the OU for a short time, it already like regularizes the distribution enough that you could just apply the previous result. And running the forward process for a short time, this is just equivalent to like running the original SGM algorithm, but just early stopping. Instead of running the reverse process all the way, just stop it like a little bit early, and then you get this kind of quality. So with this, like I feel like this covers literally any distribution you would see in practice, because every distribution in practice is compactly supported. So it's just like a testament to the power of diffusion models, as long as you can learn the score, which is a big caveat. All right, I think this is basically what I said. We can this shows you can sample from pretty much arbitrary data distributions, provided you can learn the score. And this actually shows that there's a surprisingly like principled justification behind the use of diffusion models in deep learning. Yeah, I'm not going to do the proof. So this slide is just to say, like, if you're familiar, then there's like with these like stochastic processes, there turn out to be like other stochastic processes. In particular, there's something called the underdamped or critically damped or kinetic Langevin. These are like variants of Langevin that have been used to get improvements in the sampling context. In our paper, we give some kind of like preliminary evidence that using these processes actually does not speed up SGMs. That's all I'll say about that. Yeah, this is the takeaway. Accurate score estimation means that you can sample from arbitrary data distributions with just polynomial complexity. Thank you. These are the works it was based on. Actually, like the results I showed for the diffusion model, they're like a bit stronger than what's in our current archive version. We're planning to upload a new revision really soon. And there's this like kind of mess where like after we uploaded, then like we found out about some prior work with a reference that we missed, which used similar technique. And there's a paper that came out right after us, which had also very similar results. So we're also like in the process of sorting out that mess. And just a quick advertisement, if you're interested in these questions about like log concave sampling, then I'd like to mention that I'm currently writing a book on this, which you can see on my website, here to learn. Okay, thank you. That's all.
Well, I know we bothered you a lot with some questions during the talk. Are there any questions? Yes, one question for me is for, do you, for the approximating the score function with the neural network, I just want to make, I think I didn't completely understand one part. So you have n time steps, capital N time steps.
Yes.
And are you training that neural network with each one of those time steps?
Yes, correct.
Okay. Okay, so is that the biggest computational burden here, because you want to take capital N large enough?
Yeah, so I mean, learning the score, of course, is very expensive. But score-based models are also expensive at evaluation time. So I guess like for any big neural network thing, you should expect nowadays that, oh, they're going to like use like hundreds of GPUs and train for 3 months and kill like 2 rainforests, just to learn the score. But now let's say I've learned the score and then I want to generate images. One, I mentioned that diffusion models can be slower than GAN. And the reason why is for GAN, we just run through the neural network once and you have an image. But for these diffusion models, you need to, like every iteration of the sampling algorithm, you need to run the neural network for the score function. So because of that, it can be much more time intensive. And so what people do in practice is they take really long time steps because they want to do as few evaluations as possible. In fact, they take like 10 to 15 steps for the diffusion, which is crazy to me, but it's crazy that it works.
Yeah.
Yeah, so that's the downside of diffusion models. As I mentioned, they're much more stable than GANs, which have this minimax training.
Yeah, I mean, if they can get by with just in on the order of 10 to 15, then
yeah.
All right, not really much thing to speak here.